Okay, let's get started. Happy Monday. Day today, sunny.
We could get it. Not going.
So today you want to talk something very useful and amazing. After talking about neural network and how you can learn features automatically from data, you might think, oh, that's amazing. So we don't need more job as a robotic engineer. Just gonna give everything to data, and the system gonna learn all features. But it's not always as optimal as possible, because sometimes you want to start learning noise. Learning noise. That's something that happened. So today we're going to talk about that. Also, we want to talk about if you have more than two classes. What about we have 3 classes? What about we have more than 1 classes? Like, for example, in that application, that project that we are started, like a lane tracking and road detection, sometimes you want to design a model to detect the road and recognize it with grass, for example, or other things. We have enough sensors for those. We know, for example, LIDAR can detect softness of objects. Also, we know we have other sensors that they can help us to detect the type of the object, the surface, that but there are more than 2. Most of the time, we have many type of classes that we want to classify, and today we're going to go through them and see how you, as an engineer, robotic engineer, you can play with this data to detect more than just 2 classes. But if we are going to more than 2 classes, we need to know a little probability. So we're gonna learn a new loss function. We call it Cross-Entropy. I'll talk about that. That's very useful. Lots of loss functions. The type of loss function that working with likelihood of being, for example, road, likelihood of being the ball. So computing likelihood, and we're going to see what is likelihood in general. And we're also going to talk about the things that I started at the beginning, that when we have overfitting. Overfitting means your model learn noises instead of detecting nice patterns. It's gonna learn noises in your data set. Your data set gets something wrong in your data set probably, or it's not something wrong, it's because we didn't consider that as a possibilities. So we're going to talk about those as much as we can. We're going to go before starting about deep learning. We need to know about these things because it's happening a lot. Okay, first we're going to start with cross entropy. Oh, and you feel this too, please. Cross-entropy. Probably you heard entropy word, like as a word a lot. Entropy. What entropy means? When you hear entropy, it's something that coming to your mind is just uncertainty, isn't it? Uncertainty is entropy. And maybe another thing that come in your mind is the second law of thermodynamics. No, the second law of thermodynamics is about entropy, and saying in a system always entropy increase or stay stationary. It's not decrease. So entropy always increase. That's the second law of thermodynamics. I always was thinking that's one of the law of Einstein, but it's not. Rodolph is a guy that. Okay, anyway, this is about the loss function that we want to talk about. So probably you got the idea. This loss function gonna measure uncertainty. Uncertainty between two set of data, and that's amazing. Uncertainty is something that we are always dealing with in robotics, and in this kind of loss function, we are measuring difference between actually this uncertainty or distribution of this uncertainty between what? Between true data and prediction data or predicted. So this difference can be measured using how? It's a little complicated, but as much as we can, but we're gonna use it anyway. So the formula for cross-entropy is coming from this. Maybe you say, oh, what log doing here? I'm gonna let you know why log we have that. But normally, when you want to measure cross something, so you multiply them together. Cross means involving together. So we multiply y and y hat. Well, we have here class. K is for class. It means we have more than two class. If we have just two class, we don't consider that, because if this is belong to this class, the rest is belong to the other. So we don't have K anymore. But when we have more than two classes, we consider K here. So this entropy, this loss function, is kind of measuring how for prediction, because it's true data, we know K, because somebody labeled data. Somebody say, oh, this is road, this is grass. And this is, for example, I don't know, tree, building. So somebody put these K numbers, like 0 for 0, 1, 2, 3, whatever. So we just multiply y hat with y. We have K because we have class, and I is the normal data. Thank you so much. Where's my pencil?
Sorry, I stole it.
Yeah, I just want everybody to put the same color. That's why I put my pencil. Okay, so that's the reason of cross. We multiply them together. Why we put log? log function is amazing function actually for us. Log has multiple characteristics. If we want to draw log, let's see if I can draw log. This is log function. Maybe minus log, because log is negative like this. And this is minus log. This is x. But this is, you can see, oh, okay, and this is not x, this is y hat. So it means if y hat, remember we are still in classification. This is y hat. We are in classification. So we are in classification means what? Means when we are predicting something, and if this prediction gets smaller, so generally speaking, this log function just kind of not exaggerate, but penalize wrong prediction. Penalize. Those are real apples?
Yes.
Really? Oh my God, they are so nice.
Would you like one?
Oh sure, yes. What kind of apple they are?
I don't know. I picked them from a friend's farm. There's a couple little spots, but those are okay to eat.
Oh, wow. So nice. Smell good. I love apples actually. That's why you brought them in the class.
I was just a little hungry.
Beautiful, no? Apples are amazing fruit. Look at that. It's so pretty. Nice. I love apples. Anyway, interruption. Sorry. So that's for cross-entropy. So this is as much as I can tell about that is that. So normally you are doing cross, means you are multiplying the prediction with the true data to make cross, combine them, and add them together. They are just, this y is just 1 or 0, because this is belong to this class or not. And log of that is something between 0 and 1. Between 0 and 1, show how much is belong to this class or not. So that's something that we want to find. And this loss is actually working with probability. Why? Because this is going to change to probability. How? For a class I, for a class, for example, I, for a sample I, class K, y is 1. Because we labeled them. We know this is for that class, so this is 1. And what is this y hat? Y hat is telling us actually the likelihood. This is the formula of likelihood. Likelihood of y belongs to class K. Okay? So this is likelihood. So anybody knows what is okay? So maybe I explain my. So a likelihood is the probability. If you want to define likelihood, I wrote it somewhere. Yes. When we are talking about likelihood, we are talking about the model and data. We want to see what is the probability of data actually given the model, probability of data, observing data, maybe observing data, given a specific model. And this is exactly the same. Y hat is telling us, in this case, when we have multiple model, Y hat telling us what is the probability of Y belongs to class K. What is the probability of observation data given the specific model? The specific model means W and Xi. So this conditional probability is actually likelihood. Maybe you saw this conditional probability different way as well. I don't know how much you learn probability, but in robotics, we use probability a lot and a lot. We also have this one, P of, for example, X given Y. If the Y is observing data and X is the model, maybe X and W, for example, or just W maybe. Model, sometimes we want to compute the probability of this model giving these observations. This is called posterior density. This is called posterior density. We're gonna see this later. Posterior density. Posterior density is actually the basic of so many estimation. It's actually the best estimation is posterior density. Best estimation. But it's so complex to compute. It's so complex. It's saying, okay, probability of this model given this data. How we compute that? It needs lots of relationship between W and Y. That is hard to compute. But in probability, we can find the proportion of that. Proportion of that is actually from the likelihood and prior information. I'm not going to talk more about that. So this has two parts. One, likelihood, one this, and another one actually prior information. Prior information. I'm not going to go deep on that, but maybe another time. So we're not going to talk about this part. This posterior density is not something that we're going to talk today. We're going to talk about likelihood. Likelihood of what? Likelihood of this data belongs to this model. Likelihood of this. So this is likelihood. Okay, so that's why I wanted to bring it up. So from cross-entropy, we're gonna change it to likelihood. So the formula gonna change. The formula gonna change the so this from cross that we mentioned, the y gonna get disappear because it's O1, and this y hat gonna get likelihood. So we're gonna have log of this likelihood. Log of likelihood. And if the likelihood be exponential, that most of the time is, log of exponential gonna cancel each other, and that's why we use log over there. The reason that put log over there is that because log and exponential are friends. They cancel each other most of the time. We use them together. That's why. However, when we go further, you can see how this is gonna work together. They are fit together very nicely. So, okay, so this is the loss function that we're gonna talk. The formula for loss function gonna get to this point. This is the formula that we're gonna learn, not this one anymore. This is the simplest version. So, as you can see, is a log of likelihood, and we just need to maximize this log likelihood. So the best W star, the optimal W star is the maximum or argmax, because we want to find W, argmax of this log likelihood loss function to find W. And this is maximum, also called maximum likelihood. Even called maximum likelihood estimation. This is the very general, well-known method of estimation called maximum likelihood. We want to mix this likelihood maximum and find W based off that. I don't want to go deep on that. It's so much stuff to cover if we want to go there. But we're just going to use it. Okay, so the last part is this. Why we use log? Because log kind of penalize confidence and also penalize wrong prediction. But this penalization is in a good way. And encourage model to assign high probability to the correct class. So let's see how we can use that. That was just about cross-entropy. So the cross-entropy, if I want to make it just short, is a kind of loss function that you're going to use it when you have different class. And you want to find likelihood of belonging to those classes. Okay, and multi-class regression. Right now that we know that's a kind of loss function, we can talk about multi-class regression. In multi-class regression, the neural network, instead of having just one neuron at the end, has multiple neurons at the end. So in normal neural network, you had one neuron here that gives a score. And most of the time, we use just sigmoid function to make it between 0 and 1, or tangent function to -1 to 1 to make it similar to the likelihood. And you might have hidden layers and data that coming from here, for example. This was the normal neural network that we had before for two-layer neural network, one hidden neural network. But in this case, if you have multi-class, instead of having one score, you have multiple score. And you need a function to make these scores like a probability. And that function is called softmax function. As you can see in this picture, the softmax function get the result of these three outputs and make them as a likelihood shape or probability shape. How is doing that? It's using exponential family. So exponential and log are very similar in some shapes. Exponential is like that. Y is equal to e power x, for example. If this is x, this is y. So it's going like that. And is again exaggerating or penalizing x. When the x increases, it makes it, exponentially bigger. And to make it to normalize it, we divide it for sum of all the classes. K is a class. Remember. Okay. So normally, softmax not doing so much things. It just put the exponential there and also normalize it. How normalize it? We divide it by this sum of all classes together. The point is, we want these last layer values sum to 1. add to 1. When we add them together, become 1, because probability need to add to 1, because we want to say, okay, probability of being grass is 20%, and road is, for example, 70%, and the other is 10%. If we add to 100%. I think so, 7, 20, 90, and 10, 100. Good? So we want that. That's the reason of using this softmax function. So this is the softmax, and it's gonna all probabilities positive first using this exponential. As you can see here, exponential is just in the positive part, and also the total probability sum to 1. That's the reason of using this softmax, and also give the probability shape. Yes. This is not just probability, this is likelihood. Why is likelihood? Because it has conditional, and we are finding the probability of this data, yk, belong to this model. When I'm talking about model, means w and x. X is features in a simplest way, but we should put phi of x here as well if you want to specifically talk about features. But if it's x, is the simplest case of features. Okay, so we have this, and what we need to do, we need to learn. So after this function, so remember, in neural network, we do pass, forward pass first, based off the previous parameters. We get y hat, we compute y hat here. What is y hat here? This probability is y hat. And we got this probability in softmax or y hat, and then we go back propagation. We do back propagation, compute loss function. How we compute loss function? Using cross-entropy loss. That's why I talk about cross-entropy loss first. Why we use cross-entropy loss? Because they are set together. It's get probability, and it's cross-entropy. You also use probability. And this log function is playing amazing here because you have exponential family here. Log and exponential are going to cancel each other, and derivative of that going to get so simple because it's just exponent going to stay. And what is exponent? Just z of k. And what is z of k? It's just this. However, we add that with a value for make it more stable. I didn't mention here, but in the code, you can see that. Okay, that's, I think, enough things to know about two amazing things. First, cross-entropy, and then softmax. You don't need to memorize too much about it as far as you know what's going on here and what is likelihood, why we use log here, and how log can penalize the confidence and stuff is enough. But I want you to can use it in applications like this. Applications that you're going to see them later in this class and in real work or life. Like, for example, here we have, we want to have a model. We want to learn a model to detect different classes of terrain. Like you have asphalt, you have gravel, you have grass, for example, and or even more. But here, imagine we have 3 classes of terrain areas, and we want to learn them, and we want to detect them. Like in the application of self-driving car or autonomous robots, if the robot knows what is the environment, terrain can help to navigate better. If it's, for example, muddy or is gravel, or is very smooth or is not smooth. So this information can come from this application. It's very amazing application. I hope one of you guys work in this as a final project, especially in LiDAR part. If you are interested, you can work in that. So normally, for this kind of applications, we can use three types of sensors. We can use IMU. IMU give us some information about the type of train because it can measure vibration. Because normally inertial measurement unit, IMU, can measure acceleration. It can measure angular velocity. And even sometimes can measure like magnetic field. But these informations are enough for us to see how we can find the vibration signature of the environment. Because if there is like lots of vibration, this change of acceleration and angular velocity can measure that. This is one of the factors that we can consider. This is one of the actually features that we can access. That's why we put them in an X. Another thing is coming from another sensor, from LiDAR. LiDAR normally can measure surface roughness. Roughness of, oh, I already wrote here. Roughness of surface coming from LiDAR, you can measure that. And is with analyzing again variation, when the laser going and come back, you can see these differences in different surfaces can be measured. So normally LiDAR can measure surface roughness as well. Another type of sensors that you can use for terrain classification is wheel encoder. Wheel encoder is when you are estimating velocity and so normally you can compute a slip ratio. So wheel encoder measure velocity based off the turning the wheel. So if you compute a slip ratio normally is the velocity of reading from wheel minus the actual velocity of robot, and divide by velocity of robot. So this is giving you guys enough information about the texture or the surface of the place that robot moving. So these three measurements or these three features are enough for you to learn to train the robot for moving in different environments. Any question about this? You might use more other sensors as well, but these three are enough. Even just one of them might be enough. If you're just working with LiDAR, maybe just work with LiDAR. LiDAR give us enough information regarding the surface, and you just can learn from that. Because LiDAR give lots of information, extra information. But fusing them together also is amazing because it gives you more observation or makes the system more observable. Okay, what about the model? For each class, So we have three classes. We have asphalt. Maybe I should put this 0, 0, 1, and 2. Because in the code, I wrote the code here, I put 0 and 1 and 2, but here I put 1. Doesn't matter. So we have 0 for asphalt, 1 for gravel, and we code them, and 2 for grass, for example. So, and the model is like that. So the measurements coming from class K is WK transpose X, and X is this, plus a certain constant bias, that this bias is regarding to that K. When we have K, means that is related to that specific class. Okay, because we train the model, so it means we know K, we know this data is labeled data. So to do softmax layer, we put that in a soft. Okay, what we are doing right now, we are moving in a actually forward pass. We are moving in a forward pass, so it means we start with a W, initial W, and find W and B, because here we have bias 2, and we find this probability based of these values, and if we back to the picture that we had last slide, we had softmax here, and softmax get values from these three classes, and these three classes coming from input X. Okay, so this hidden layer, we don't have hidden layer here. We are just considering directly W. But in a, if you make it 2-layer, we have W and V. But here I wanted to make it simpler. We just have W. So here we have three classes. K is 1 or 0, K is 1, and K is 2. And softmax is doing there. Softmax give you these probabilities. Why we compute these probabilities? Because in backpropagation, we're going to use it in loss function. Okay? So let's go for backpropagation. So normally we need to find maximum likelihood. So this is how we find y hat. So we use cross-entropy, and cross-entropy, because this probability is exponential, log is helped a lot here because it's gonna cancel out each other, and just exponent's gonna stay out. The exponent part is just z of k. Z of k is exponent part. So let's write the code. So I think this, yeah, I'm gonna make another assignment for you guys based off that. So this code, it's good to understand it good. So, okay, let's see what we are doing here. We are, first of all, generate synthetic data here. We are making three classes. So one for asphalt, one for gravel, one for grasses. As you can see, we are doing two-dimensional data. We are making two-dimensional data. We are making some multivariant normal distribution. This is multivariant normal distribution. Multivariant means there is more than one variable. It's two variables here, two-dimension, because we have x and y. Multivariant is that. Multivariant, because they are random variables, they are normal distribution random variables. So we are generating some random numbers around the mean with some covariance. So the mean is here, for example, maybe maybe I should draw this lower. Here is 2, not 2, 0.2, sorry. 0.2, 0.2, 0.2, 0.2. That's the mean. And what is the covariance? Covariance here is this. We use identity matrix and multiply that with this number. So here is 0. This is 0.2. So it means they are varying this much around the mean. So they are varying this much around them. So we have something like that. How many numbers? 150. I'm explaining this completely because you're going to use it. So try to learn. If you have questions, ask me. So we are generating this data belonging to the class asphalt, for example. But in real situation, you need to use this with the real data that coming from, I don't know, LIDAR, whatever sensor you have. If you just want to use one, for example, sensor. You just need to get lots of information about that, manually label them, and make this. But we are here to make the life easier. We are creating this data. It's creating data called synthetic data. This synthetic data for asphalt is like that. For gravel, we put another mean. The variance are all the same. Covariance here, because we have two variables, is called covariance. The difference between variance and covariance is that covariance is a matrix that diagonal is the variance part. So that in that matrix, 0.02 is the variance, because variance is for x. These two off diagonals are variance of x and y, because we don't have correlation. There is no correlation. That's why it's 0. That's why this circle is, that's why this data is circle. If there is correlation, this gonna get shape gonna change to ellipsoid. We had that before in first of the class when we talk about norms, remember? They are important. Anyway, we just make it simple. Let's go for other data. Other data is for gravel. For gravel, for example, we have, this is here, for example, 0.7, 0.4, oh, 0.4, a little higher here. Okay. Okay, so here, and another data, for example, this is for this. Can you see the yellow? Yeah, it's a little hard to see. And then for the other one, we have, this one was 0.7, 0.4. This one is 0.4, 0.8. This is also, the covariance are the same. Okay, we create these three sets, and then we label them. This line, this is the label. We label them. This is making a vector, including zeros, n1, n2s. And n is 150. This is y. This y is a label that we created. So we created the y because we want to give those data label. This is the label that we created. 0 for asphalt, gravel, 1 for gravel, and 2 for grasses. Okay, so the creating data is done. Now we go for softmax. So in softmax, there is things that we need to consider. In softmax, we always, when we do exponential family, we eliminate it from the max. And this is actually helping for to stabilize data. So this is also something that we consider here. Don't surprise if this is not exactly same as what I mentioned. It's just here Z is x minus max of x. So this elimination makes the data a little more stable. So the other parts are the same. So that's the softmax formula. And the rest we give label to data based off this y. And we do initialization. I should clear this. Okay, let's see if that's, yeah, it's not visible. I have the picture anyway. The picture is here. And then we go for training. How we do training? We do 500 epoch, and we do forward pass and computing gradient, backward pass. The gradient is just exponent part. It's easy. And then update and repeat it. And as you can see, these colors in these points are coming from the data. And the result of this code is the background. Is the background part. Those colors are the result of that. For your assignment or for your project, also, if there is a classification, I want that background from you. The rest is already given. That background is learned. However, I didn't put the visualization part, but visualization part, I'm gonna